This video is going to cover finding zeros of polynomials. I'm going to start by giving you a theorem, the factor theorem. This theorem says x equal a number, x equal k, is a zero, and a zero of a function is a solution to that function equal to zero. So a number is a zero of a polynomial if and only if x minus the number is a factor of the polynomial. Let's use this theorem to solve a problem. Let's see an example of how this works. Show that x plus 2 is a factor of the polynomial, then find all other factors. So x plus 2 is a factor if x equal negative 2 is a zero. That means if I take the polynomial given, which is f of x equals x to the third minus 6x squared minus x plus 30, and I divide that by x plus 2, I should get a remainder of 0. If x plus 2 is a factor and x minus 2 is a 0, then we have to get a remainder of 0. So I'm going to use synthetic division to do this. I'm dividing by x plus 2, so I'll put a negative 2 right there, and then I put the coefficients of my polynomial, 1, negative 6, negative 1, and 30 inside my box. I bring down the first number, so I brought down the 1. I multiply, 1 times negative 2 is negative 2. Add, I get negative 8. And then we repeat the process. Minus 8 times minus 2 is positive 16. I add, I get 15. One more time. 15 times negative 2 is negative 30. We add, we get 0. Because I have a remainder of 0, x plus 2 is a factor. This means I can factor my polynomial as x plus 2, and then these numbers on the bottom are what I have left over, or I should say coefficients of what's left over. If we divide the x plus 2 out, we're left with a 1x squared minus 8x plus 15. And now I can continue to factor to find the other factors and then the other zeros. Let's see, I need product of 15, sum of minus 8, 5 times 3 is 15, and if they're both negative, adds up to negative 8. So my polynomial can be factored as x plus 2, x minus 5, x minus 3. This also means that x equal negative 2, x equal 5, and x equal 3 are zeros of that polynomial. Let's do another example. Find all zeros of the polynomial. F of x equals x to the fourth plus 2x to the third minus 7x squared minus 8x plus 12, given that x equal negative 3 is a 0. If x equal negative 3 is a 0, then x plus 3 is a factor. So I'm going to divide by x plus 3 using synthetic division. I put the negative 3 outside of the box, and I put the coefficients of my polynomial inside the box. Bring down the 1, bring down the first number. Now I multiply. 1 times minus 3 is minus 3. Add, I get minus 1. Minus 1 times minus 3 is positive 3. Add, I get negative 4. Negative 4 times negative 3 is 12. Add, I get 4. Finally, 4 times negative 3 is negative 12. Add, I get 0. That has to happen. I have to get a remainder of 0 since negative 3 is a 0 of the function. So now we have technically divided or factored out that x plus 3, and we're left with a 1x to the third minus 1x squared minus 4x plus 4. I'm going to try to factor the remaining polynomial. Because there are 4 terms, I'm going to factor by grouping. First 2 terms, I can take out an x squared, and I'm left with an x minus 1. Second 2 terms, I can take out a negative 4, and I'm also left with an x minus 1. That means we can pull the x minus 1 out front, and we're left with an x squared minus 4. So now we have this factored as x plus 3, x minus 1, x squared minus 4. We can factor this x squared minus 4 further. That's a difference of perfect squares, and it can be factored as x plus 2, x minus 2. So now I've got my polynomial in factored form, 4 factors, 4 zeros. My zeros are negative 3, positive 1, negative 2, and positive 2. The next theorem I'm going to give you is our rational zeros theorem. This theorem says all rational zeros, and a rational number is something that can be written as either a whole number or a fraction. So all rational zeros of a polynomial are of the form p over q, where p is a factor of the constant term of that polynomial, and q is a factor of the leading coefficient, or the coefficient of the term with the largest exponent. So let's see what this theorem is saying, or how this theorem works, by looking at a couple of examples. List all possible rational zeros of each polynomial. First example, f of x equals x to the third minus 4x squared plus 3x minus 6. Okay, so p is factors of the constant. The constant is a 6 or a negative 6. Sign doesn't matter here. 6 is divisible by 1. You can divide it by 2, by 3, or by 6. So the possible factors of our constant, the p, would be positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 6. Q is factors of the leading coefficient. The leading coefficient is 1. 1 is only divisible by 1. So possible rational zeros would be 1 over 1, 2 over 1, 3 over 1, or 6 over 1, and they could be positive or negative. So that's positive or negative 1, positive or negative 2, positive or negative 3, and positive or negative 6. My second example, we've got the polynomial f of x equals 2x to the fourth plus 7x squared minus 3x plus 5. P is factors of the constant. 5 is only divisible by 1 and 5. Q is factors of that leading coefficient, which was 2. 2 is only divisible by 1 or 2. And those factors could be positive or negative. So I have to do every possible combination of p over q. So it could be 1 over 1, or 1 over 2, 5 over 1, or 5 over 2. And each of those zeros could be positive or negative. So I've got plus or minus 1, plus or minus a half, plus or minus 5, or plus or minus 5 halves. If this polynomial has rational zeros, it has to be among that list. All right, so let's see how this theorem is actually useful. Let's say we have a polynomial f of x equals 2x to the third plus x squared minus 4x plus 1. We want to find all zeros. But this polynomial can't be factored, and they didn't tell me what any of the zeros are. So I'm going to use my rational zeros theorem to make a guess. P, factors of the constant, are just 1. 1 is only divisible by 1. Q, factors of 2 would just be 1 or 2, and they could be positive or negative. So my possible zeros are either 1 over 1 or 1 over 2, and it could be positive or negative. So I've got 4 possible rational zeros. So I'm going to start by just making a guess. What if my zero is x equal 1? I'll use synthetic division to check. I know it's a 0 if I get a remainder of 0. Okay, so I copy down the coefficients of my polynomial in the box. I'm dividing by x minus 1, so I put a 1 outside of the box. Bring down the 2. 2 times 1 is 2. I add, I get 3. 3 times 1 is 3. I add, I get negative 1. Negative 1 times 1 is negative 1. I add, and I get 0. So I got lucky this time. I happened to guess correctly on my first try. And so that tells me I can factor my polynomial as x minus 1, 2x squared, plus 3x minus 1. And so if I want to find all zeros, I can set this factored equation equal to 0. And now I just have to solve 2x squared plus 3x minus 1 equals 0. I can try to factor this, but I don't think we can actually factor this one. However, it's a quadratic, and I can use my quadratic formula. I know that x will equal negative b plus or minus b squared minus 4ac all over 2a. And so I plugged in 2 for a, 3 for b, and negative 1 for c. That gives me negative 3 plus or minus 9 squared minus a minus becomes a plus. 4 times 2 times 1 is 8, all over 4, or negative 3 plus or minus root 17 over 4. So I have 3 zeros, x equal 1, x equal negative 3 plus root 17 over 4, and x equal negative 3 minus root 17 over 4. These 2 zeros I got from the quadratic formula are not rational zeros. They're irrational because they have the square root in them. And that's why they didn't come up in our list. Next theorem, lots of theorems in this section, is known as the fundamental theorem of algebra. This theorem says if we have a polynomial of degree n, so largest exponent is n, then it has to have exactly n linear factors. So a 4th degree polynomial can always be factored into 4 linear factors. A 5th degree polynomial always has 5 linear factors. And the factors are always of the form x minus a number, x minus c, where that number, c1, c2, c3, are complex numbers. So what this is saying is an nth degree polynomial can always be factored into n factors. It's just sometimes your zeros are going to be complex numbers. Not all of your zeros will be real, but we can always factor it if we allow ourselves to use imaginary or complex numbers. So here's an example. Let's find all zeros and write as a product of linear factors. This is a 4th degree polynomial, so it should have exactly 4 factors. I'm going to start by using my rational zeros theorem to make a guess. The constant is 8. 8 is 1 times 8 or 2 times 4. So it's divisible by 1, 2, 4, or 8. My leading coefficient is 1. So my zeros are 1 over 1, 2 over 1, 4 over 1, or 8 over 1. And they could be positive or negative. I'm going to start by making a guess. I'll guess x equal 1, and I'll use synthetic division to check it out. So I put the coefficients of my polynomial inside the box. I'm dividing by x minus 1. X equal 1 is my 0, so it goes outside of the box. Bring down the first term. 1 times 1 is 1. I add, I get 0. 0 times 1 is 0. I add, I get 2. 2 times 1 is 2. Add, negative 2. Negative 2 times 1 is negative 2. I add, I get negative 10. The remainder is negative 10. That means this is not a 0. Unfortunately, I guessed incorrectly. So I'm just going to try something else. What about x equal negative 1? So coefficients are still in my box, but now I'm going to divide by x plus 1. So bring down the 1. 1 times minus 1 is minus 1. I add to get negative 2. Negative 2 times negative 1 is 2. Add, I get 4. 4 times negative 1 is negative 4. Add, I get negative 8. Negative 8 times negative 1 is 8. Add, and I do get that remainder of 0. That tells me that x equal negative 1 is a 0. And I know I can factor this as x plus 1. And then 1x cubed minus 2x squared plus 4x minus 8. So now that I've factored out the x plus 1, I'm going to see if I can factor the remaining polynomial by grouping. It's got 4 terms. That's why I'm going to try grouping. So give myself a little more space. So first 2 terms, I can pull out an x squared. I'm left with x minus 2. Second 2 terms, I can pull out a 4. I'm left with an x minus 2. So the x minus 2 goes out front. I'm left with an x squared plus 4. And then we still have this factor of x plus 1. So I've got x plus 1, x minus 2, x squared plus 4. If we're trying to find zeros, we're setting this equal to 0 and solving. So each of the factors could equal 0. If x plus 1 equals 0, x equals negative 1. If x minus 2 equals 0, x equals 2. If x squared plus 4 equals 0, that means x squared equals negative 4. This is not going to give me a real number, but I could write the solution to this as an imaginary number. I take the square root of both sides, don't forget the plus or minus, and the square root of 4 is 2, so the square root of negative 4 can be written as 2i. So I've got 2 imaginary zeros, plus or minus 2i. So I found all my zeros. They're at negative 1, 2, 2i, and negative 2i. Each of the factors will be of the form x minus a 0. I would also like to point out that anytime you get complex zeros, zeros with i's in them, they always come in pairs. And they always come in what's known as conjugate pairs, where one of them is going to be a positive I and the other will be a negative I. We'll say a little bit more about that later. Okay, so the factors have to be x minus the zeros. So x minus negative 1, that's x plus 1, x minus 2, x minus 2i, x minus negative 2i is x plus 2i. And so here's my 4th degree polynomial. It has exactly 4 linear factors. It just happens in this case that 2 of those factors have complex zeros in them. Let's do one more example. Use the fact that x equals 2 plus I is a 0 of f of x equals x to the 4th minus 6x squared plus 12, I think I said that wrong, x to the 4th minus 6x to the 3rd plus 12x squared minus 6x plus 5. We're going to find all zeros and write this as a product of linear factors. So first of all, x to the 4th means we're going to have 4 zeros, 4 linear factors. All right, I'm going to use synthetic division. It turns out we can use this synthetic division with imaginary numbers as well. The work's just going to be a tiny bit messier. So if x equal 2 plus I is a 0, we should be able to divide x minus the quantity 2 plus I out. So I'm going to use synthetic division, and hopefully I get a remainder of 0. So I bring down the 1. 1 times 2 plus I is 2 plus I. Now when I add, notice you can only add the real parts and then the imaginary parts. So minus 6 plus 2 is minus 4, and then I still have this plus I. Now I have to multiply. I have to take minus 4 plus I times 2 plus I. I'm going to have to use FOIL on that. 2 times minus 4 is minus 8. Outer would be 2i. Inner minus 4i. Last plus I squared. 2i minus 4i is negative 2i. And this I squared turns into a negative 1. So finally, if I combine like terms, minus 8 plus minus 1 is minus 9. So we're left with minus 9 minus 2i. I'm going to write that down in my box. Okay, add. 12 minus 9 is 3, so I've got 3 minus 2i. We're going to multiply 3 minus 2i times 2 plus I. We're going to have to use FOIL on that again. So I'm taking the 2 plus I times the 3 minus 2I. Using FOIL, first, 6. Outer, 2 times minus 2I minus 4I. Inner, 3I. Last, negative 2I squared. I can combine minus 4I plus 3I to give me negative I. Minus 2I squared. I squared is negative 1. That becomes a plus 2. I can combine the 2 with the 6 to get an 8. So 8 minus I. I'd put that in my box. Add. Minus 6 plus 8 minus I is 2 minus I. Multiply. So now I'm going to do 2 minus I times 2 plus I. First is 4. Outer, negative 2I. Inner, positive 2I. Last, negative I squared. The i's cancel out. Minus 2I plus 2I, that cancels out. Negative I squared becomes a plus 1. 4 plus 1 is 5. Oh, and this worked out. Minus 5 plus 5 is 0. I have a remainder of 0. But I'm left with something that's a mess. The coefficients of this polynomial have complex numbers in them. But it turns out that complex zeros always come in conjugate pairs. If 2 plus I is a 0, the conjugate of that is going to have a negative I in it. So it's always a plus or minus I. So 2 plus I is a 0. Its conjugate would be 2 minus I. Just change the sign of the I. So let's, without even rewriting this ugly polynomial, let's do synthetic division again. Let's take this result here and divide it by the factor x minus the quantity 2 minus I. So I'll bring down the 1, multiply. 1 times 2 minus I is 2 minus I. Now when I add, notice the i's go away, and I'm just left with negative 2. So we'll do negative 2 times 2 minus I. Negative 2 times 2 minus I should be negative 4 plus 2I. The i's cancel out again, and I'm left with negative 1. Negative 1 times 2 minus I is negative 2 plus I. That adds up to 0, as it should, because 2 minus I is also 0. And now I'm left with a polynomial that's a little bit easier to work with. So basically, I have shown that we can factor this as x minus 2 plus I, x minus 2 minus I, and then we're left with 1x squared minus 2x minus 1. Give myself some more room. So the quadratic that we're left with is something that we can solve to find our remaining zeros. I don't think we can factor this. We're going to have to use a quadratic formula again. We'll take negative b, so negative negative 2, plus or minus b squared, negative 2 squared, minus 4 times a, which was 1, times c, which is negative 1, all over 2 times a. That gives me positive 2 plus or minus square root of 4, and then minus a minus becomes a plus 4 all over 2. So this is 2 plus or minus root 8 over 2. 8 is 4 times 2, so root 8 can be written as 2 root 2. And then we can simplify because we can divide 2 divided by 2 is 1, 2 divided by 2 is 1, so we can write this as 1 plus or minus root 2. All right, so there's my zeros. X equal 2 plus I, x equal 2 minus I, x equal 1 plus root 2, x equal 1 minus root 2. Notice that irrational zeros, things with square roots, also come in these conjugate pairs with plus or minuses in them. So there's my 4 factors now. I can take x minus each of these zeros to get my 4 factors. They look ugly, but that fundamental theorem of algebra told us because it's an x to the fourth, we have to be able to write it as 4 factors. So my factors are x minus, technically it's minus the quantity 2 plus I, so x minus 2 minus I, x minus 2 plus I, x minus 1 minus root 2, and x minus 1 plus root 2. All right, that was my last example. As always, please let me know if anything in this video is unclear.